Yes, am I audible? Nabila.
Yes, sir.
Uh, okay. So, in the last class, we stopped at this point and this question was completed. We had to start with potential energy difference. See, potential energy difference means that when potential, we talk about potential, two terms are there. One is only potential energy, one of the terms is only potential energy. Now, when we say only potential energy, this means the potential energy between infinity to some point P. Okay, from infinity, we are bringing the body to some point P. That was the potential energy. That's why we did that calculation in that manner. Okay, the whole calculation, entire calculation is put in that manner. So, potential energy means you are bringing something from infinity to your respective point, whatever point you have chosen. Then you have potential energy difference. Now, how it's different? This is from one point to another point. So that's all the difference. What you have to keep in mind. Rest of it is exactly the same. The meaning and everything that we've studied. So here also in between we'll choose a small point. This like this, a very small point will be chosen. Okay. And instead of this point being at infinity, we'll have this point at some distance of r. That will be the difference. Okay, this point will be at a distance of r1. Second point where you have to get the object, that will be r2. So see here again we'll write the equation of work done. Okay. Now here work done will be force into displacement integrating from r1 to r2. That will be the difference. In the previous derivation yesterday, what did we see? We saw that that was from infinity to the point r. Now this is from r1 to r2. Is still equal to g capital M small m by x square. We will put this value over here. So work done will be equal to capital G capital M small m by x square dx, integrating from r1 to r2. Okay. Now, look, when you take common g capital M small m and 1 by x square, we already know that is equal to 1 by x. Remember, x to the power minus 2 dx, we integrate from r1 to r2. Then this becomes equal to g m m x to the power minus 1 from r1 to r2 and with this minus sign. Then we bring this back to the denominator. That is 1 by x from r1 to r2. Now what do we do, class? We put in the upper limit first and then the lower limit. See, this is the same thing which we did yesterday also. But one of the limits were infinity. Right? So this will be minus z capital M 1 by r2 minus 1 by r1. This is the formula of potential energy difference. See, this will be potential energy difference. Yeah. Potential and potential difference have this major difference. Is it clear to all? Okay, please write it. Then we'll start with gravitational potential energy. Does also done?
Yes, ma'am.
Yes.
Okay, see, coming to potential. Okay, that was intensity. Coming to the potential. Potential is actually a scalar quantity. So whatever is this work done that we have talked about, when we take that work done per unit mass, that is known as the gravitational potential. Okay, so it is the work done in carrying unit mass from infinity to point against a gravitational field. Means same thing, but work done per unit mass is known as the gravitation potential. Okay, so all these things are connected only in from infinity or bringing a point. But when we said what's the total work done, that total work done was converted into potential energy. Now work done per unit mass is known as the gravitational potential. Okay, force per unit mass was intensity. Remember, force per unit mass was intensity. Work done as it is stored in the form of energy is the gravitational potential energy. And work done per unit mass is gravitational potential. Are all these 3 points clear to all? Look, intensity is force by mass. We discussed this. Work done gets stored in the form of potential energy. Okay, that was GMM by R, which we did minus GMM by R, in fact. Okay, and see, this was intensity. When you have the entire work done getting divided per unit mass, that is what is known as the gravitational potential. In all the cases, the mass is being brought from infinity to a particular point. Okay, like you have your source mass, this is placed at some infinity, this source mass is there, and you have a unit mass. Unit mass is being brought from infinity. This is the unit mass, this is being brought from infinity. 1 unit is there, 1 unit means 1 kg is there. This is brought from infinity to the point P. Okay, near the source. Some point is put here. Now, potential of mass at the P point we have to calculate. Okay, this potential at the P point of mass. Now, when you talk about the potential, it's work done per unit mass. And if you make mass as 1 kg, potential becomes exactly equal to the work done. This means work done in bringing mass from infinity to the point P. This is what is being written because it is per unit mass. Scalar quantity, SI unit is joules per second. Now, how can you define gravitational potential? You can say, see, when I'm writing, the potential is equal to work done per unit charge, mass, sorry, not charge, work done per unit mass. And as soon as I make mass as 1 kg, M is equal to 1 kg, potential becomes equal to the work done. When potential becomes equal to the work done, what can you define potential as? Potential is the work done in carrying a unit mass from infinity to a point. Is it given? Carrying, yes, the same definition. Now see, now got it? Why is it used? Work done in carrying unit mass from infinity to a point. So this is the formula for the gravitational potential. These 3 differences should be remembered and should be clear, then you'll be able to understand what is the intensity, gravitational field. See, this is about the field, this is about the energy, and this is about the potential. These are the 3 topics that we have seen, and these 3 topics are very confusing. Make it somewhere on the corner of your notebook or anywhere so that you remember this is how you have to follow, and then search for the heading accordingly. Okay, so gravitational potential for different objects are different. That I'll discuss. First, you copy it till here. Are these 3 differences clear to all? Intensity, energy, and potential. Clear?
Yes, ma'am.
Okay. Others also?
Yes, ma'am.
Okay, please write it. Okay, class, different objects. Let's remember the potential of it. Derivation is not this. So the way you have remembered it for the intensity, remember it for the potential as well. Okay. So gravitational potential of a point mass is minus G capital M by R. All right, potential difference will be minus G. See, why is it? How are we getting this? Basic reason, it is work done divided by the mass. Now see, if I have the work done minus G capital M small m by R, and I divide mass further, so what will be the potential? Minus Gm by R. That's why we are getting the first one like this. The basic for a point mass minus G by M. Okay, minus G into M by R. Potential difference will be minus G 1 by R2 minus 1 by R1. Okay. Now, when we talk about the hollow sphere, there are 2 points that you have to, actually there are 3 points that you have to take. First is the outside one, where the point is lying outside the sphere. Your formula is very simple. You take the separation from the center to this point of calculation class. Okay, that is R. So the potential becomes minus G M by R. Then you have the point at the surface and the inside part, which is exactly the same. From the inside portion, when you reach the surface, it is minus G M by capital R. Because this is all related to potential, so even in the inside portion for a hollow one, potential will be existing. Okay, it won't be zero like the field. I hope you remember for the field. Those who have not revised, revise these 3 topics properly, otherwise it will be confusing. Though it's a very easy chapter, don't make it confusing on yourself. Field part, gravitational field part, gravitational energy part, and gravitational potential part. Just segregate and properly solve them. Okay, so inside part and surface both will have the radius. See, this is the radius. When I say capital R, this is the radius, and when I say small r, this is the separation. What's the difference between separation and the radius? Separation is from the center to wherever the point is situated. From the center. While radius is what? Radius is the radius of the sphere. Whether the point is exceeding it or coming inside it, radius will be fixed. It is constant. We know this already, that radius is constant. So that's the difference between the separation and the radius. Outside the separation will come. Separation means from the center, wherever the mass is put, you're going to calculate the entire distance. Okay. Radius means radius is for the inside surface. You know what the radius means. Then see, there is one more case at the center. Now, in this case, the center isn't zero. It is minus 3 gm by 2r. This one. Minus 3 capital G capital M by 2r. Now, when you talk about the solid sphere, here the surface and inside are different. Okay. Minus G by Gm by R is the same. Minus Gm by capital R is the same. This is still the separation, and this is still the radius. There is no difference in this. But your inside gets separated, and there's a huge tough derivation for this. You need to remember all the formula. So minus capital G capital M into 3 capital R square minus small r square divided by 2r cube. So this is a formula which you have to remember, class. Okay. And center one is 3 by 3 gm by 2r. That is 3 by 2 the surface. And this is an important relation. One question came in one of the schools also. That surface was given and center was asked. This is important and it's included. You can see this. Inside rarely comes, but if inside comes, it is simple formula based questions. There are no tricky questions from all of these. Okay, I'll tell you this. There are no tricky questions from all of these. But for that, you need to remember the formula properly, class. Okay. Now, the gravitational field, energy, potential parts are over. There are some extra topics like escape velocity, orbital velocity, geostationary satellite, and all Kepler's laws. All these are there. So those are the portions that we have to discuss. And I hope in the next class, we'll be able to complete this chapter and soon start with solids. Okay. But write down this first, and if there's any difficulty, please revise this chapter. Intensity, energy, and potential can be confusing. And then the laws from here, Newton's law of gravitation is very easy, and then the variation of acceleration due to gravity with depth, height, and rotation. All right, please write it. Okay, see, let's come to escape velocity. Have all of you written or still writing?
Uh,
Writing or done?
Done, mom. Done.
Oh, see, what is escape velocity? Basically, when an object has to leave the surface of the earth. If an object is there, this is the surface of Earth. Now, see, as Hafsa asked me, I think last week, that what is this height if it is at a certain altitude? So that is motion under gravity. I think it was you, Hafsa, who asked this. Similar to
Yes.
motion under gravity, right?
Yes, ma'am.
Huh. So see, for that only, when the body is moving at a certain height, when it has crossed the atmosphere of the earth, there is a certain velocity that is required by the body. If that velocity is achieved, then only it will be able to escape the gravitational pull of the earth. That velocity is known as the escape velocity. See, term only is telling you what is the escape velocity. The escape velocity will be the velocity that is helping to escape the atmosphere of the earth. Atmosphere in the sense the gravitational pull. Let's say till here only, earth is able to exert its gravitational pull. Okay. If Earth is able to exert its gravitational pull, then this part has to be overcome by certain velocity. If it isn't, let's say velocity is very less, it will go to some height and it will come back. Like when you launch rockets cross the gravitational pull of the Earth. So because their velocity is fixed, okay, fixed at a certain level. So minimum velocity with which a body is projected so that it just escapes the gravitational pull of the earth and the body will finally stop at infinity. It is said to be that it will stop at infinity. And you know where is infinity? At infinity, right? So escape velocity of the earth is 11.2 kilometer per second. This value you have to remember. All right. Now, when we are talking about the escape velocity of the earth, kinetic energy is equal to half mve square. Okay, escape velocity is used. Also, kinetic energy is equal to v capital M small m by 2r. This, how is it possible and all? I'll tell you later. Right now, just remember it. So both the kinetic energies can be equated. So we can say half mve square is equal to g capital M small m by 2r. Right? So this m will be gone from here. Capital G, capital M. Okay, this is the gravitational pull of the earth. See, we'll use potential energy. Yes, Hafsa?
I'm 2 also cancel, right?
What?
We'll divide 2.
We'll divide?
That also cancel. Oh, 2 is not there. Oh.
No, that's what I was saying. See, on the surface of the earth when it has crossed, so then the potential energy is acting. Then you don't have the kinetic energy initially at a separation. So basically, the kinetic energy will get converted into potential energy. Okay, so that's why I was about to cancel it, but this will be left in. So kinetic energy will be converted into the potential energy. Okay, because it is when the gravitational, when the body is here, then there is a gravitational force between the earth and the body. And when it moves away, so this gravitational potential energy actually gets converted into kinetic energy. So that's when you will have kinetic energy as this potential energy. And now you can equate. So escape velocity's formula is very simple, I believe, 2gm by r under root. Okay, this is one formula, one very important good formula for it, where this is the escape velocity. Now see class, there was a formula of the acceleration due to gravity which we discussed. Yes, what was it? Tell me. When we discussed the acceleration due to gravity, what was the formula?
G is equal to capital G M by R square.
R or R square?
R square.
R square. Very good, Afsa. C, small g is equal to, others also should remember this, those who are not. Gm by R square. Okay. Gm is coming here. So I think I can write Gm as small g into R square. Since here I am getting this term, so I think it's better so that this can be replaced through this. Now let's put in the values here. So the escape velocity will be equal to 2 small g, right? Okay, we have taken this as small r, I have put. This will be capital R, radius of the earth, no? So capital R. Let's take here also, then only it will be uniform. At one place, small r, other place, capital R is incorrect. So capital R only let me take, which is representing the radius. So look, this will be 2g capital R square divided by capital R, right? This is gr square. This is 2. So what are we getting? This gets cancelled. Escape velocity is equal to under root 2 gr in terms of the acceleration due to gravity. Okay. This is in the terms of acceleration due to gravity. Okay, so this is what your gravitational escape velocities. Now we know 2, we know g, that is 9.8 meter per second. Radius of Earth is also known, 6,000 kilometer. So when you put in the values, no, here for escape velocity, 2 into 9.8 into 6 into 10 to the power 6 under root. This value comes out to be 11.2 kilometer per second. Okay, this comes out to be kilometer per second. Remember, escape velocity is independent of the mass of the body and it depends on the mass of the planet, because in the formula, small m isn't present. This is the mass of the body. Capital M is present. That is the mass of the respective planet. So what is escape velocity? Have you all understood?
Yes, ma'am.
Okay, Aisha, explain me, what did you understand? Everything is there in front of you. What is escape velocity? What did you understand from this? Aisha.
Uh, when an object needs to like leave the surface of the earth or any planet, the
Yes.
velocity is needed to push it. Or
Okay. Not surface, gravitational pull. Okay.
yeah, gravitation.
The gravitational pull. Very good. See, she is right. When body needs to move away from the gravitational pull of the earth. To overcome that, a minimum velocity is required. That velocity is the escape velocity, whose value is 11.2 kilometer per second. This you need to remember. Also, you need to remember these two formula. That's all. Okay. Now, is it clear to all of you or not?
Yes, ma'am.
Ikra, Nabiha, understanding?
Yes, ma'am.
Please copy this. Let's see a question based on this. This is using the concept of black hole. Okay, see how this will be used. Concept of escape velocity means you know the formula of it. So V is equal to 2gm by r under root. Now see, to cross the black hole, I hope all of you know this, that
Ma'am,
the
your
speed
voice
will
is
be equal to the
breaking.
speed of light. That is, voice is breaking.
Yes, ma'am.
Still, it's still breaking.
Now okay.
Now it's better. You just let me know if it breaks. Okay. So speed will be this, then you have to calculate the radius. Okay. So when we put in the value, r square will be equal to 2gm by v square. Sorry, r will be equal to 2gm by v square. In fact, you can use the smaller one because mass is unknown, mass of the body is unknown. Use the shorter one. V is equal to 2gr under root. This way, V square will be equal to 2gr, R will be equal to V square by 2c. That is 3 into 10 to the power 8 whole square divided by 2 into 9.8. So this much meter will be your answer. The only concept that had to be used was this and the other formula of the escape velocity. That's it. So your escape velocity should be equal to the speed of light. Otherwise, black hole can never be crossed. Okay. Write down this question. Then one more. Let's see. See, this says the body is projected with a velocity v, which is greater than the escape velocity. You have to find out the velocity with which it moves at infinity. See, initially, what will be the kinetic energy? Half mv square. Finally, what will be the kinetic energy? Half mve square, because it has escaped, right? So if I take the change in the kinetic energy, this will be half mv square minus half mve square. Let's say the change in kinetic energy is equal to some half m v dash square. Okay. V dash we have to find out. It says no, calculate this velocity. So let's say let this velocity be V dash. Now put it, half mv dash square is equal to half mv square minus half mve square. Half m will be cancelled. V dash square is equal to v square minus ve square. So V dash will be equal to V square minus VE square under root. Yeah. What did we do? See, change in kinetic energy is something. It says the body is projected with a velocity V. So initial kinetic energy will be half mv square. If it is projected with a velocity V, this will be the initial kinetic energy, half mv square. Now, if it has escaped at the end also, the escape velocity is there. This will be the escape velocity that will remain as the final velocity. This will be the change in velocity, the change that is coming. So this is the change in velocity. So we put it in the equations. We get V dash as under root V square minus VE square. Clear? Write it. Now that completes with escape velocity. Satellite is left. We'll start with satellite. There you have orbital velocity. One class is required to complete this chapter. Okay, please write it.
Ma'am. Ma'am.
Okay.
Ma'am, this change in kinetic energy,
Mm-hmm.
why you wrote 1 minus kinetic 1 minus kinetic 2? Because it's final minus initial, right?
Yes. Yes. Wait. This will be VE square. Correct, Hafsa. Right. Final minus initial. It is. Change we are calculating this minus this. So VE will come here. And this will be the V. Right, Hafsa. Okay. Thank you. Fine. Please, others also make the correction. Change we are calculating, and this is kinetic energy. It will always be final minus initial because we are not calculating any loss. Only in cases of loss of kinetic energy, we calculate initial minus final. This will be final minus initial.
Ma'am. Ma'am,
Yes, Afsar.
ma'am, this velocity is greater than escape velocity, right? In question it's given. So, but answer is coming.
No, see, when you calculate kinetic energy, no, with kinetic energy, you always have a modulus. Okay. Whenever you have the modulus present in kinetic energy, it's there. So even in this question, if we took this as v square minus ve square or ve square minus v square, answer would have been the same because kinetic energy will never be negative. So it will always carry a modulus with it. Okay, so that's why I said it is technically final minus initial, so I changed it. But when you wrote no v square minus v square, that was also correct because in kinetic energy it's a scalar quantity. So you'll always have the modulus. That's what I was saying. In only in loss of kinetic energy, there's a problem where you have to be careful. Got it? The kinetic energies and work done. These two things you can have you'll always have a modulus. Potential, no, means potential will be negative. Negative can be there, positive can be there. Negative can represent your bounded or attractive system. Fine?
Okay, ma'am.
All right, class. So this we'll complete in the next week. One topic is there, means one class is needed, not one topic. 2 to 3 small topics are left like these. Okay, we'll complete this in the next class now. All right. Okay. Thank you.